Hello students, welcome to the next chapter on operating systems, main memory. In this chapter, we'll talk about the main memory management concepts, the allocation or memory management techniques, along with a few examples from Intel and ARM architectures. Through this session, we'll study a detailed description of various ways by which we can organize the memory management hardware. Then we'll see different techniques for memory management, which may be contiguous or non-contiguous. Non-contiguous will include a discussion on paging and segmentation. And we'll go through case studies on Intel Pentium architecture that will support the pure segmentation or the segmentation with paging concepts. In this part 1 of the memory management series, we'll discuss the basics or the backgrounds of the memory allocation, the memory protection concepts, the address binding schemes, the dynamic loading and the dynamic linking of the memory. Okay, going back to the basics, we know that for any program to be executed, that needs to be brought into the main memory because CPU can directly access the main memory as well as its internal registers. Whether there are 10 programs or 20 programs, all of them had to be brought from disk into the main memory for their execution. A program could have been written into any sort of a language, but that needs to be converted into machine or binary instructions for their execution. Okay, so the CPU basically uses, or the system generally uses, the fetch, decode and execution instruction cycle in order to execute one instruction followed by the other as guided by the program counter. For memory, there are two basic types of instructions. One is read, another is the write operation. In case of a read operation, we need to know which location of the memory the data has to be accessed. And in case of the write operation, in addition to the location of the memory, we also need to send the data which has to be updated into that location. Hence, the memory would see only the stream of address plus read requests or the address plus data write requests, as we could see here. Okay, so there are two basic types of access. One is address followed by a read request, rather in the same way. Okay, and the other one would be the data as well as write request along with some specific location of the memory. Generally, the read request is indicated by some load kind of instructions of the CPU, in which the data is accessed from a particular memory address, say 20010, and fetched or loaded into the CPU register number 8 or accumulator or anything. The write kind of a request will require the memory address, for example 1090, along with it will send some exact data bytes which has to be updated from CPU registers into the memory location, say 1090. Memory generally doesn't know how these addresses have been generated. Hence, this is the responsibility of operating systems memory management unit that will generate such kind of addresses where the exact data information has to be accessed from or updated into. So these things, when we do process the memory access, the access to every CPU register can generally be done in a single clock cycle or less because the data is already inside the CPU itself. Vis-a-vis a single cycle access of the registers of the CPU, a memory access may take more than one clock cycles. So when it takes more time to access the memory, CPU in the meanwhile can get stuck just because it doesn't have the required data available with it in order to proceed with the execution of instruction. This kind of process is known as stall. So in order to avoid this stalling, we can have a faster memory component specialized and installed into the system that is known as cache memory, so that it could avoid some delays of memory access by pre-buffering or pre-caching some additional regions of the memory copied into this cache memory, which generally operates at the speed of CPU access. So this can help us deal with this stalling issue. In addition to the stalling and cache, we also require to ensure that the user processes cannot access the memory allocated to the operating system processes or the resident OS kernel processes. And similarly, the process generated by one user or one program should not be allowed to access the processes or the memory allocated to the other processes or other programs. So this concept is known as protection of memory. One of the methods to ensure memory protection is with the help of two basic CPU registers. One is called as base register, another is called as limit register. A base register will hold the minimum possible address allocated to any process, whereas a limit register would hold a value which indicates the number of memory addresses allocated to a process. As can be seen in this diagram, there is a total memory of 1024 multiplied by 1000 addresses. That means 1024,000 addresses memory available in this system. The memory region from address number 0 till 256,000 is allocated to the operating system, and remaining memory would be left for all the user processes. As we could see in this diagram, there are three processes generated or allocated to the memory. The first process starts from the memory location 256000. The second process starts from the memory location 300040, and the third process starts from the memory location 420940. So these three values 256000, 300040 and 420940 become the respective base address for each of these three processes. Talking about the second process, the base address shall be 300040, and any access that is generated or any address of the memory which is generated by process 2 must be limited to the range 300040 till 420940. So all access requests from the memory region 300040 till 420940, less than 420940, they all would be considered as the valid access addresses for this process, whereas any access beyond the limit, that means to the limit of memory addresses less than 300040 or the memory locations onward 420940 would be treated as invalid memory access request for this process. Let us try and understand how this works. A CPU generated some address, and this address value is compared with the value of the base register. So if the CPU generated address is greater than or equal to the value of this base register, it would be treated as a valid access, and if this condition is not satisfied, it would be considered as invalid memory access. Now, if it is found that the CPU generated address is larger than or equal to the base address, then the next condition would be checked is the value of this address against base plus limit. So if this CPU generated address is subsequently less than or equal to or rather less than the base plus limit, in that case this would be validated as the correct access, or otherwise it would be validated as an invalid access request. So in case the access request is invalid, a trap would be issued to the operating system monitor and it will be generated as an addressing error. Let us now discuss the address binding mechanism. As we know that a program would be having a set of instructions, and all these instructions have to be loaded into the main memory at some place. For the sake of simplicity, what the system can do is assume that the first physical address of every program will start from the address location called 0. Okay, so this 0 would be a very convenient because anything increased beyond 0 to find the offset would be easy and a simple addition. So this might not require much of the hardware or software support, but when it comes to this implementation, it is rather not practically feasible that each and every program has to start from a location 0, because when it comes to multi-programming, then a lot of data has to be moved in and out of memory or shuffled within the memory itself. because when the CPU is switching from one program to the other or one process to the other, then every process starting with 0 might not help. Okay, so generally the systems would provide some hardware or software support in order for memory management. So there can be different ways by which this memory management hardware could help in binding the addresses to different elements of the program. Okay, so the first thing could be the source program can have all the addresses represented symbolically in form of variables. For example, a variable count can be used to represent some memory location. So now the program or the source program, the user will just access or manipulate this value with the help of the variable called count. Say count is equal to 0, count is equal to 100, count is equal to count minus 10, or count is equal to count plus 1, or count is something used in read mode or the write mode. The compiler would be typically responsible for binding these symbolic addresses to some kind of relocatable addresses. When I talk about relocatable, it means this address could be mapped onto any location in the program at every different execution instance. Maybe for first execution instance, this memory allocation or memory address represented by the variable count could be 1096. At the another instance, it could be 2841 or any other valid access based on the memory which is allocated to this program. Okay, for example, in this case it's written like count is some variable which is 14 bytes from the beginning of this module. Okay, then there is a linker or a loader that will try to bind these relocatable addresses to actual physical addresses or absolute addresses, which are the precise address given in the main memory. Like we are talking about 74014 would be the actual address which is allocated to this variable count in the main memory. So generally this binding mechanism is nothing but mapping of one address space to the other. Okay, so this is what we generally talk the address binding as. This address binding of instructions and data into the memory can be done at multiple stages or different stages. Number one, it could be done at the compile time, or it can be done at the time of loading, or it can be done at the time when the program is executing. So in case it is done at the compilation time, that would be feasible if you already know in advance what is the memory location which should be allocated to any program in the main memory. Such kind of a code generated by the compiler in which the memory locations are known a priori or known in advance, this kind of object code is called as absolute code. And in case this code needs to be recompiled if the base address or the starting address of this program is changed. The second instance of mapping could be done at the loading time. When you do the program's address binding at load time, it means every time a program is brought from the disk into the main memory, it will decide what are the addresses allocated to various program elements. Such a code is generally known as relocatable code, because this generally tends to assume some base address for this program elements, and a relative access to individual element with reference to the base address can be used. Then the third type of binding could be done at execution time, wherein the memory addresses generated for different program elements or variables or any components would not be determined unless and until that program is actually put into execution by the CPU. So in this case, the binding is delayed until the runtime, because in this case the process can be moved between the memory from one location to the other, and it might not affect the pre-written code to a great extent. So this gives us a little flexibility in moving the program from one location to the other during its execution. Okay, so this would obviously require some additional hardware support for address mapping, and this would be done in terms of a dynamic base and limit registers. Well, this diagram will help us understand the flow of the program execution and the address binding done. Okay, the source program, once given to the compiler, if the compiler is doing the address binding task, it would be done as the compile time address binding. Okay, similarly, this object code is generated, and this object code would be further given to the linking editor or linkage editor that will also combine or link multiple other object programs associated to this program. Okay, and it will generate a loadable module, and this will generate the load time addresses when this loadable module is passed on to the loader. It will also link some system libraries along with this particular load module. Okay, so once this program is actually loaded into the memory, if the memory allocation or address binding is done in the execution time, then this can also be possible during the runtime binding or dynamic linking or dynamic binding of this dynamically loaded system library programs could be done. I hope you could recall the access in form of the DLL, dynamic link libraries in Windows. Okay. This address binding will now lead us to two different types of addresses. One is called as a logical address, another is the physical address. A logical address is the address as generated by the CPU, whereas the physical address is the address as seen by the memory unit. A logical address space would be the set of all such logical addresses which are generated by the CPU or the program, whereas the physical address space would be the set of all addresses actually allocated to that program in the physical memory. Generally, the logical and physical address spaces would be the same in case we are using the compile time or we are using the load time address binding scheme. But in case we are using the execution time address binding scheme, then the logical address space would be identified as the virtual address space. The memory management unit is such a hardware device or the implementation which will help to map this logical or the virtual address space onto the physical address space of the main memory. Okay, so there are different methods which are possible for conversion of a logical address onto a physical address. These would depend upon the type of memory allocation that we have followed or adopted. Generally, the user programs will deal with logical addresses because it would hardly be concerned about what exact memory location has been allocated to a particular variable or a program element. And while the program is actually executing, in that case, whatever task is done by CPU has to deal with the physical addresses only. So that means the logical address space must be bound to the physical address spaces. One such method that we can use in order to implement the memory management unit would be the base register or a relocation register method. In this case, the base address of the memory allocated to this process would be stored into a register called relocation register. For example, in this case it is 14000 and a CPU generated a logical address is 346. So this 346 would be considered as an offset value and this would be added into this relocation register value. So it will generate a new address called 14346, which will be the exact location into the main memory where the desired data value is stored. We believe that the entire program has to be brought into the memory at all the time for its execution, but most of the time the applications do not use all the set of modules or the program features available in that application. Okay, so in this case, loading the entire program to the memory well in advance is considered as the wastage of the memory space. Okay, so this could also reduce the multi-programming degree of the computer, because if unusable or non-required program segments are loaded into the main memory, then this main memory would run out of space for additional programs. There is a concept which is called as dynamic loading, which will defer the transfer of a program module into the main memory or a copying of the program module into the main memory unless it is actually used or called by the program. Okay. Likewise, there are modules of the same program which are not used every time, so we could implement dynamic loading over there. Similarly, there are certain modules which are already available or already brought into the memory, and they can be used by a current program. So this can avoid duplicity of the same code segment to be used in multiple applications. For example, if we have the application of Microsoft Word, Microsoft PowerPoint and Microsoft Excel running together or loaded into the main memory at the same time, because the user is working on three different documents or three different files, one related to each other. And each of these three applications might be using a component called spell checker. So spell checker is implemented as a common library for all these three applications. So if each of these three applications uses a separate copy of the spell checker, it will multiply the space required by spell checker to 3 times. Rather than multiplying it by 3 times, what system can do is system can load one copy of the spell checker somewhere into the memory, and this single copy of the spell checker can be dynamically linked with each of the three application spaces. That means Microsoft Word would also be dynamically bound to the memory space address allocated to the spell checker. The same memory space allocated to the spell checker can be dynamically mapped or dynamically linked with the Microsoft Excel memory space, and the same memory space allocated to the spell checker can be dynamically linked to the PowerPoint application space. So this kind of thing could be implemented in form of dynamic linking, and dynamic link libraries or the DLL files in Microsoft Windows, as the case be, could be implemented. So this is linking rather than loading, which is postponed till the execution time. This is what we call as dynamic linking. Dynamic linking is implemented in this way. So generally some small piece of code or stub is used to locate the appropriate memory resident library routine, and this stub will replace the address of the routine and execute that routine. So operating system will check if the routine is in process memory. If it is not in that address space, it will be added to the address space. If it is already there, it will proceed with the further execution. So dynamic linking is generally useful for the libraries, which are also known as the shared libraries once they are generated by the system. So in subsequent videos on memory management, we'll discuss the contiguous memory allocation techniques, the fragmentation and non-contiguous memory allocation techniques of paging and segmentation. Looking forward to join me up in the next session. Thank you for watching.